Hi everyone and welcome to today's session. So for today, we'll be continuing what we did last week, which is to try to find a good representational space so that you can learn from it and potentially encode memory into such a space such that it can be reusable and you can learn very well from very limited experience. So today, mainly we'll touch on how to do the bias and generalization part, how to perform them in a hierarchy, and also whether transformers could actually do this hierarchical representation already. So let's begin. This is just a recap of what has been done last week. So one way to do representational learning is to compress it into a bottleneck and then reconstruct it. So this kind of loss is a reconstruction loss, typically by like mean square error in the pixel space in the image here. And the problem with this is that you will try to remember everything. So if you look at this number 4 here, all right, you try to remember all the specifics of this 4. So if you come with another 4 like that, you also need to remember all the specifics of this 4 and try to construct again here. But that may not be the aim, because what you want to do is you want to map all of this 4s into a common space in the manifold here, such that regardless of how the 4 looks like, it will be represented as a 4. And then maybe here you have another like cluster for 3 in this manifold space in the bottleneck. So this kind of approach, if you try to reconstruct the input domain, is probably not the best because you can remember everything. You have to remember everything in order to do well. So then we talked about like how we could do better. And perhaps you don't have to predict everything in the input space. Like for driving, you don't have to predict the leaves moving on the trees because it doesn't affect how you drive well. All right, what you should predict is how the other cars move, whether there's any pedestrians walking or not. But how do we tell the model what is important to predict? Okay, so one way to do it is to do like in the transformer way, where you have like initial tokens, like for example, the cat set on the, and then you try to predict the next token. So like for example, mat will be like 0.9, floor maybe 0.1. Yeah. So by doing so, we are trying to learn the structure of the input here. And only the things that matter for this input will be used, okay, to predict the next token. So in some sense, by doing this self-supervised, or some people call it unsupervised learning, by doing this self-supervised learning, we can actually learn more about like what is important here to learn. So like if we look at the example behind, like in the previous slide, the driving of the car, because the way the trees sway is of no consequence to how you drive, all right, you will eventually learn to filter it out. And then you focus only on predicting the things that are important. Okay? And this will actually help a lot with generalization because you don't have to remember like how the trees move. So next time you drive on another road with different kind of background, like different kind of trees, you can still use the same concepts you have learned, okay, in this kind of road here, because the background is irrelevant. You already know, like in your abstraction space, you only focus on the road, the other cars, you know, those kind of stuff are reusable. You don't have to focus on things that don't really matter for prediction like all this. So next time you go to another road, you don't have to like relearn. Yeah, if the road is like a similar curvature, you already know what you need to do. So I'm saying that transformers, or rather the kind of prediction where we predict the future, predict the next token, could actually help to learn the representational space better than the autoencoder. So just move on quickly because this is just a recap. We do have other things like fixed biases that help us learn faster, okay, because the world is high dimensional. And if we want to learn everything from scratch, like we need to learn how to interpret this high dimensional signal, we might take forever to learn because there's just too many possibilities of learning. So one way to ground our learning to make it faster is to have fixed biases. Like for us, for sound, we hear it by frequencies because the cilia in the cochlea will vibrate at certain frequencies. So in some sense, you are doing some Fourier transform when you like hear the sound through your ears. Same thing for our eyes. We actually see red, green, blue in patches by the cones, and we see black and white for the rods at night. So this ground our sensory inputs. So instead of seeing like 25 colors, like maybe the manta ray sees 25 colors, we just focus on red, green, blue. And perhaps red, green, blue is already sufficient for survival. We don't really need to see infrared, ultraviolet, microwave, X-rays, you know, that kind of, we don't have to see all this. Yeah, right now in our world, just red, green, blue is enough. So we filter in the very, very wide electromagnetic spectrum. We filter only to like this very narrow visible light spectrum, which could help with learning much faster. So if we identify, like this one, nature has identified for us through evolution. So you can narrow down what you need to learn using fixed biases. And overall, the representation that I thought of is something like that. You have an input, your fixed bias will help you to represent it in a better way, a more concise way for learning. You do your next token prediction, which is like in the processing step here. You do your next token prediction in order to, or the next token prediction to find out the structure of the world. So in some sense, next token prediction would like give some structure of the world, and that may be why transformers work so well. All right, then of course, last week we also talked about this. Like you also have this reverse process that could happen, that you could reverse back to the input domain. For example, if you want to like do like a painting, you need to remember what you see. You could do a reverse representation of like what the world is. Okay, and the output here, you want it to be in the same domain as the input. Okay, but this actually is not very good because, you know, if you do fixed biases, you kind of filter out, like over here, if you filter out only the red, green, blue kind of light inside here, you can't really construct back you might lose out what you filter on in fixed biases. So in general, the loss between the input to output, if you reconstruct back, is not exactly a very good loss, but, you know, for some cases, you might need to do it. And I also argue that if we were to look at like modern image techniques, because we try to reconstruct back into the pixel space, we necessarily don't really represent it that well in the representational space, because the reconstruction loss is not a very good loss to tell you about the structure. So perhaps what we need to do is, instead of just trying to reconstruct back the input domain, like for example, vision and audio, right now we focus a lot in reconstructing back the original domain because of like use cases like image segmentation or audio generation. But for decision making, maybe we just need to get this output space here that cannot be like really reconstructed back to the input. Okay, but it will give you a very, very concise and compressed representation for decision making. Right. So this is the recap so far. Okay, so before I move on to like what I'm going to cover today, any questions so far on the recap or any clarifications you want to make? Okay, all good, right? So let's move on to the crux of today.
Wait.
Oh yes, sorry. Yes, please go ahead.
So, you remind me of no free lunch theorem, like just now you stated. So the bias make you not be able to learn something. Sorry, the bias makes you have been capable of efficiently learn something at the expense of not being able to learn something.
Yes, correct. You filter out some information which is irrecoverable.
Yeah, okay, that's all. Just remind me of that. Yeah.
Yeah, definitely. So we might be very good at certain stuff, but, you know, if we have a decision-making task that involves us finding out like whether or not a room has an X-ray or not, we would suck at it because we just don't have the capabilities to do it. But
because I just listened to one episode of the ML Street Talk. Like one of the person they invited is Noam Chomsky, the linguist. Yeah, so
very famous
he
guy.
also talked about that. So basically, he's saying like but that is like the focus is on the natural language. So it's the same idea. Being able to learn something implies like you
forget
must
something.
have been able to lost the ability to learn something else. Yeah.
Yes, I mean, in information theory as well, the way we process like information through a channel, you realize the information content actually drops as you like do like more of the like decision making. Because in order to do decision making, maybe the outcomes is like binary or ternary or like there's like fixed classes. In order to process the information from like input domain, which is like pixel space, into like one of the classes, you will lose a lot of information because once you get like, let's say this image here is a 1. Let's say this image here is a 1, and you classify it to the category 1. All right, so you classify it to a category 1. In order for you to progress from this set of images to the category 1, you must lose the information about the pixels already, because from this category here, there's no way from this category you could like reconstruct back the original one here, because the amount, the pixel, you translate the pixels a bit, the one could be a bit distorted. You don't know because you only know the category, but you cannot go back to where your input domain is most of the time, which means that if you want to make a decision or you want to make like some processing of information, you necessarily need to lose information. And this information is most of the time irrecoverable. Yeah, so anyway, I'm saying that the representational space likely lies somewhere here, like in between here. You must lose some information here, and then you can get some abstraction space here. And in fact, what we will see today is that we may not only just have one abstraction space, we can have multiple abstraction space. All right, that's the idea of the hierarchy. And we can choose the abstraction space that we want to solve the problem at hand. So if the problem is like trying to reconstruct the one itself, then your abstraction space maybe is the input space itself, which is inefficient, but it's possible. I mean, you have to dedicate a lot of your memory to it, dedicate a lot of your like effort to learn stuff, to like memorize the entire input space. But it's possible. But most of the time, what we do, we will do somewhere in between, like over here. Abstraction space will say that, oh, image comprises of one horizontal line and like one diagonal line and one vertical line, something like that. Yeah. So you could like express it in terms of strokes. So maybe a better way is strokes. So this could be an abstraction space that could be used to like learn other stuff. Like you can use it to learn letters, you can use the same strokes again. Yeah, but for different tasks, you have different abstraction space. Go a bit more to the input, you have pixels. Go a bit more to the output, you have these categories. Yeah, so I believe that this hierarchy is very important, and knowing which abstraction space to choose is also very important for the task at hand. All right.
One thing I would say is that the statement here in the yellow box, fixed bias helps to speed up learning. So I'm not exactly true as well. It really depends on.
Please say your point of view. Yeah.
I think if we are talking about fixed bias to the particular learning algorithm, right? It actually helps, if you're assuming that you did it correctly, it helps to converge to a better optimal, but it's hard to say whether you're speeding up the learning. Because if you mean speed up the learning, in my understanding is like, for example, lesser epochs in the training, that may not hold. Some fixed bias, like for example, when we do the chunking, I show you that it takes very long to actually converge, right? But if you train long enough, it converges to a better local optimal. So it's not exactly true that it helps to speed up learning.
Yeah, but you actually doing chunking like in the pixel domain here, like you group neighboring pixels together. That is actually an algorithm used to process information, yes. But I mean, in terms of this fixed bias I'm thinking of, it's more like to filter out what is important. So instead of like maybe taking in all the ultraviolet X-ray, you only take in RGB pixels. Or maybe for MNIST, you only take in black and white pixels. So you filter out the color. So something like that you already know this bias only focuses on the things that are relevant for your use case. If you use that fixed bias, would you say you definitely will learn faster? If you remove away information that is actually noise, it's not needed for your decision making.
I won't even agree. It's hard to say, because once you pre-process the input, right, and then you feed that, yes, you're kind of removing the unwanted information, but the rate of convergence may still be the same or even take longer depending on what you're removing and what algorithm you're using to learn the actual representation you see. So it's hard to say that, once you, like for example, you pre-process something or you have a fixed bias for a particular input, it will definitely speed up the learning.
Okay.
But in some cases, you smoothed it, yeah.
All right. I mean, I can see that happening for some use cases where you might remove too much. Then it might hinder learning. But I think for most cases, it would definitely help to speed up learning, because it's something like attention. It forces you to pay attention to what's needed, right? So it's a fixed kind of attention. Like the structure has already determined what to pay attention, what you need to pay attention to.
I think it's a matter of whether the biases you have align with the objective, right?
Yes. Yeah, actually, yeah, that's true. I think, Dylan, you might be also hinting on this point, right? Like the fixed bias might go counter to your objective.
Not only counter, but I can see that happening. So it use it with caution, I guess.
Okay, yeah. So maybe the statement can be re-qualified to fixed bias helps to speed up learning, provided bias is correct. Provided bias is aligned with objective. How about that? Can you agree
I
with
would
this?
just go with achieving a better local optima for the solution once convergence is once converge.
Sure. I mean, if you treat the local optima as your objective loss, then yes, I think it's the same statement.
As in, I guess recently you have been very interested in the speeding up the learning, I realize. But if let's say, okay, we don't exactly have infinite computation, but then we still train, we have a certain resource, right? I think the more important one is like once you allow the algorithm to find out, search out the solution space, do you still converge to a better solution compared to, on average, better to the other algorithms? Like Ziyi was pointing out the no free lunch theorem, right? Why does this algorithm its preference to this particular problem? I think that's the gist of it instead.
Okay, we'll keep that in mind. All right, so I would like to move on because actually this is the recap. So we'll move to the hierarchy part. All right. So I will go to this part. So before we touch on the hierarchy, I'd just like to recap also another kind of stuff on memory that I talked about, like one of the last few sessions. So I believe that memory right now is represented in the wrong format. I think we should just reference it in format of like reference and movement, because it's very native to a lot of different things. Like a ball right now, you move a bit, so you can represent like a science kind of thing with an initial state with a motion. So a lot of other things can be represented like number line. You start with a number, you add some number. A lot of concepts can be represented like this kind of vector representation. And so if you could like learn this kind of vector representation, you might be able to reuse it. And you can reuse basically this movement here. So like if reinforcement learning, we have a start state here. The movement can be like the action. And then the resultant state will then be like the new state here. You take the initial reference plus your movement, you just do vector addition, you can get your final state. And what's amazing is if we could find a way, okay, so this one I haven't really found yet, but if you could find a way to map this like initial reference to your current situation here, if you do a mapping function here, you might also be able to map your movement vector, which means that you can apply whatever you learn in a different scenario. Like for example, if I hold my cup in my room versus like I hold my cup in the office. In this case, the movement is the same because like this, the reference, the map should be like a one-to-one. Like I can map the reference to the current state in a one-to-one map, and the movement may be also mapped directly. Yeah, so you can then apply the same movements for the cup. Another thing that I was talking about last time is like you could do something like LLM. You have a context and you have your memory. So for example, the context is like do the opposite of this. And like the memory is John went to the supermarket. So initially the John went to the supermarket movement vector might be here. All right, then because you say that do the opposite of it, by doing some form of self-attention, you are able to use this thing here, which is the current state itself. You're able to use this to sort of influence this movement here. So I have to think more about how to do this in general, but one way of doing this projection might be just through using LLMs to just change the way that we interpret certain tokens, right? And why I talk about this here. Okay, so this is the insight that I had recently. This mapping here, okay, other than being conditioned by this current state here, okay, because a lot of times our memories are stored in like probably an abstracted view in hierarchy, because like I remember myself in a room, this room is in my house, this house is in like this neighborhood and so on. So everything is in some form of hierarchy. And this mapping here may actually be conditional, okay, on whatever hierarchy that comes above it. So like if this reference point comes from another meta state here, I call this a meta state, or rather the abstraction above your memory, you might actually need to use this meta state to condition on your mapping. So this mapping is conditioned on two things: conditioned on the current state and the meta state. Yeah. So this something I'm still thinking of, but we need to make this mapping very flexible because there's a lot of things that can be used to change and influence like this projected movement. Yeah. So there was one time I think Geoffrey Hinton was in his GLOM architecture, he was talking about this neural diffusion, or I can't remember what it is, but basically you have an input variable like x, and then this actually performs a function fx. fxa. All right, so you have a different variable a, which is like a conditional, which can actually condition like how you interpret this function f. So initially, this function fx could be like something like x plus 5. But you could actually make it like x plus 5 plus a, where a is like an additional factor that you can use to like morph your function. So the same function with different input parameters a could be a different function. So this a is like something like what you use the current state or the meta state. You can actually condition your function so that the function can be a different function. Although it's still the same function, in general, it could be like morphed to a different function. So it allows quite well to like reuse this function again for multiple situations, like just conditioning on an additional variable. Yeah, I'm thinking that we need to do something like that for memory as well. So this again is very rudimentary thoughts I have. I can't remember what's the name of this in the GLOM architecture. I have to read the paper again. If you all remember, you can let me know. I think it's something to do with neural something machine. Yeah, neural analog machine. Yeah, basically it's a function that can be conditioned on an additional variable. Even in the JEPA architecture, you also have a hidden state you can condition on. So that looks something like this as well. So I think in general, this idea is more or less what the great minds are thinking as well. So a very flexible morphological function space. Yeah, that you could even use LLMs to represent this function, Yeah, so recently Wolfram Alpha has come up with some LLM-based functions where you can define a function based on just description, like say use the active voice, then you can change whatever sentence comes as an input to the active voice. Or you can give it like few short examples like this 0 is a 0, this is a 1, this is a 0. Then what is this? Then you can use few short examples to condition this function as well. So LLMs can also represent this function. And if LLMs represent this function, then it will be something like this. So you can have this thing as an LLM-based function. So when you do this kind of symbolic architecture where you have like, this hierarchy is also linked to like symbolic AI because you represent things as graphs. So when you have graphs like that, you can represent traditional symbolic AI or traditional graphs. The relations are fixed. Okay, but with LLMs, okay, the relations can be flexible because it can be conditioned on certain variables. So if you look at the Wolfram Alpha LLM functions, this could be the new way of doing this kind of symbolic architectures. In one of my past few sessions, I invited the two guys that did symbolic AI. They are also doing something like this. They are doing an LLM-based function that can like morph the input space into the intermediate representations. So I believe this is the way ahead. You need to do some form of very flexible morphing of this kind of graph relation. And I believe this may also be how memory is stored. You can store memory at different layers, but then because of how you condition your memory above, because of how you condition your memory above to interpret the layer below, you can then get different kinds of ways to interpret your memory for new situations. And also, of course, your current state also matters. So there's two ways. The current state plus the meta level state will both condition your movement itself. So this is a relatively new idea I have. Maybe I just pause for a while if you have any clarifications or any like insights that you have with this, or you've seen something similar. Okay, if not, we can also discuss this near the end, all right? So I'll move on. All right, so this is the main crux of today's session, hierarchy. Okay, how do we represent hierarchy, and why is it interesting? Okay, maybe I start with like why it's interesting first. Hierarchies are interesting because you can reuse components below the hierarchy. So like, for example, we have like maybe a goal state at the top here. The goal state here maybe is to walk. Okay, and then in order to walk, okay, maybe at the bottom, your action representation is go left leg move forward. And then the other side will be like right leg move forward. Yeah, so you can easily see that you can also reuse the same set of things for run. Run, you move forward in a faster pace, but you can also reuse the same kind of like representations for moving your leg in an action called run. So as you can see, this kind of hierarchies here could be reusable. You learn the bottom level representation, you can use it in multiple contexts. And this is very good because this is something like compositionality, something that Geoffrey Hinton wanted to do with his GLOM architecture, where you represent part-whole hierarchies. And if you can represent part-whole hierarchies, there's a chance that you can reuse the parts in some other format in the future. Right? So something like this would be very, very crucial for fast learning, because you don't have to learn everything from scratch when you see a new situation. If you can compose the new situation into parts of what you have seen before, you will learn much faster. Okay, so let's move on to the next slide. So this is a recent paper by, I think, Meta published this in Nature. So they took some brain studies, brain scans, and they asked people to like read a book or something, and they tried to see like which regions in the brain are activated. So like, for example, you see the tokens like once upon a. So you have a brain region that activates like for the next token time. But more interestingly, we also have brain regions that activate for sequences like that time in a, and like a meta level sequence up here, like time in a dark forest, right? Which means that as you do a prediction, you are not predicting just only the next token, you're actually predicting a series of tokens over here. But one thing I like to quantify is that because if we were to only predict like a sequence of tokens, you realize that the number of possibilities will become exponentially. If you predict all these tokens, if you predict accurately or exactly, possibilities are exponentially increasing, which is not possible to do. So as you go up this prediction hierarchy, you necessarily must be more and more abstract. Because if you are not more and more abstract or more and more macro level, you will run into the problem of computational infeasibility or computational intractability. So this shows that because this is done on patients' brains, this shows that in the brain, there's a form of hierarchical prediction that is happening right now. And we may not be modeling this hierarchical prediction well enough right now in current architectures, and we might need to imbue it more, right? So that's why I say the first bullet point is more than just the next token prediction, but broader prediction at higher levels. And the higher level, the more higher you go up this hierarchy, the more abstract it is. Okay, more abstract and less detailed than lower levels. So the next thing over here is GLOM. Okay, how to represent part-whole hierarchies in the neural network by Hinton. I think it didn't work out too well because I haven't heard any results from it other than the concept paper. I think it's because they tried to do everything end-to-end differential, but I don't believe that everything is end-to-end. You probably need some memory component to it, which is not included here. Right? You need to reference external memory. Okay, so over here, this thing also tries to do like part-whole hierarchies in terms of like for each level of abstraction here, these are the levels of abstraction or like levels of abstraction. Each of them are conditioned at each time step, conditioned by the top level and conditioned by the bottom level, as well as conditioned by the same level. And then you sort of do an attention over all of them. Yeah, so this is very, very complicated. Okay, and perhaps this process needs to be simplified. Yeah. So this one over here, I think maybe we don't really need the one at the bottom. I mean, I could be wrong, but I don't think we need to condition at the bottom. We just need to condition on the same level and above. I mean, the bottom might just feed you the information, but you don't have to condition on that. Yeah, so something like this needs to be thought about, because if we want to achieve like general intelligence, I'm pretty sure we need to model some form of hierarchy efficiently. Okay, so this is a first step, but this is not a very efficient step to, this is not a very efficient way to model hierarchies. Okay, any questions so far?
How is this like the high level idea, how is it different from the classical planning? Because in classical planning, we also have this notion of hierarchy. So we can break down more complex tasks into simpler tasks. Like, for example, you want a robotic arm to grab an object, then you break it down to like the servo on different joints to move together in certain coordinated way. But like they are individual motion, right? So they also have this notion of hierarchy. How is it different?
It's the same actually. So you have more and more like actions towards the bottom end, which is more the motor neurons, right? You move your servo joint forward, backwards.
Yeah.
Towards the higher part, you will have things like move arm forward. And towards the even higher part, you have move body forward. Because if you move body, you need to move your arm and your legs, right?
Yeah. So at the bottom, they have what they call, I think, atomic action or something.
Primitive actions, I think. Yeah, that's the hierarchical RL literature. I think they call it primitive actions.
So I guess the difference might be in how do you find, like in the classical planning literature, I think how they find it is do some search. So there's no learning involved, I believe. So maybe that's the difference.
Yeah, but the problem with doing this kind of search is that if you start searching all the way at the bottom levels, it can be very, very intensive. You need to go through a lot of steps in order to find the goal. I have a slide talking about that later, so maybe we'll talk more about that.
Okay.
Yeah, so hierarchical prediction also applies to actions, in my opinion. Yeah, so here, this hierarchical prediction, all right, is predicting the next token. But as I said in the previous session, next token prediction is something like next action prediction, because in this use case, the action is to predict the next token. You can generalize it to an RL context by predicting the next action given like states. So like this is the state for the RL context. And like this here will be the action. This token will be the action. Yeah, so this is one way of next token prediction is actually similar to next action prediction. And I believe we can also learn the right abstraction space if we do action prediction. Okay, so let's move on. So this is an example of hierarchical prediction that was done by OpenAI. It's called the Jukebox Music AI. It was quite cool, okay, because what they did vector quantization. So vector quantization is a way such that you quantize like your signal here into certain vectors. So like, for example, you represent it into, this is your initial codebook. Your codebook has different vectors. And then you try to encode like your initial signal into codebooks into vectors based on your codebook. Like this like dictionary with each codebook is something like for example, vector 1 could be 0.1, 0.3, minus 0.5, and so on. You can do this. Vector 2 could be, yeah. So these vectors are typically learned through k-nearest, through basically doing clustering, and then you find the cluster centers, and then each of these will be different vectors. You then map the signal, okay, to the most approximate vectors here. So this over here, vector quantization, I believe they did the like residual vector quantization, where you start off with a vector. Yeah, I do have a slide on this later. So you start with a vector like this, maybe 0.1, 0.3, minus 0.5, and so on. You start off with a vector. You map the most relevant vector to the first signal. So like over here, you actually map the most relevant vector here. Like maybe the most relevant vector is the light blue one. So you map here, and then you take the residual and map it to another vector. Yeah. So you keep doing the quantization, okay, until you finish the entire signal. Okay, this is one way of doing it. Okay, over here, if you look at this diagram here, what they could have done, okay, because it's been a while since I last read this paper. What they could have done here is they could have like split the input signal into various parts here, and then they just quantize it to the nearest vector that represents this part. So at the top level, this is the coarse representation, okay, because it just like tells you more about like the structure of the song and so on. At the bottom layers, you have more and more fine-grained representation that maybe tell you, okay, this is the drum beat over here. And at the bottom level here, this could be like, or the vocals come in with the intonation and everything. All this will be more and more fine-grained. Okay, so over here, this tree will be 3 different views of the same song, right? And we represent it using vector quantization. So one interesting thing about how they did the generation of the music is that you can actually get more and more specific generation of the audio. You can look over here, this waveform, okay, is the most similar to the original audio as compared to like if you look at this waveform. And this waveform here is only from using the macro level view, the most general and most abstract view. Okay, you only do like for each segment of time, you only quantize it to the nearest vector. Okay, this is the signal you get. Okay, it's like, okay, if we talk about it in a cosine wave or sine wave, it looks like this. So it's just like quantizing at the most higher level. So imagine if the signal was something like that. At the top view, maybe you are quantizing like that. At the middle level view, okay, you are quantizing perhaps, okay, in a more like fine grain, a more higher frequency one. Okay, and the bottom level, maybe you quantize it in the shortest most in the most frequent part. And then you can just add all of them together, or you like condition all of them together. You could get back this thing here. Okay, and what's the benefit of doing this kind of segregation? Like you segregate the top layer, then the middle layer, then the bottom layer. Okay, you can condition things on the top layer so that you can affect the generation of the middle layers, and the middle layer can also affect the generation of the bottom layer. So there's some form of hierarchy here. You can actually reuse the same vectors here. And if the top few vectors are different, you can get different kind of sounds. Right, this is a very, very interesting phenomena, because let me just draw you this piano key context. Okay, again, I kind of forgot whether they did like residual vector quantization like within this layer here, but based on what I see in this diagram, it's probably not. Okay, it's probably just split into the time, different chunks of time, and then quantize it to the nearest vector. I'll go and check it out after this, and then let you know again. But the idea of hierarchical like quantization, okay, this doesn't change, okay, regardless of how we interpret this paper. You see over here, like here we have C, D, this is the piano key, okay, C, D, E, F, G, A, and B. So, you know, in a typical piano keyboard, you have like 7 keys per octave. Right, so of course you need to draw in like maybe the black keys here also, like that, and also here, 1, 2, 3. Yeah, so we also repeat this 7 keys here, another 7 keys, and so on, and another 7 keys. Okay, if we don't have this top level and we don't have this bottom level, this middle level, we only do it in the bottom level. You need to represent, let's say in your piano of 21 keys, you need to represent, if only one level, you need to represent 21 keys. Okay, but if you group in 2 levels, okay, your first level being you select the octave level. Okay, if you select the octave, how many octaves can we select? Okay, select 3, right? 3 octaves. And then at the bottom level, what we will do is we will then select the keys. How many ways are there to select the keys? 7. All right. So the total number of ways that we can get if we do the hierarchical kind of separation, you take 7 plus 3, you just need to represent 10 different possibilities. Because you just need to represent 3 octaves and 7 keys. Okay, with this 7 keys here, maybe you can have the octave representation as like that, plus 7, plus 14, and plus 21. And then you could have the bottom level representation as like that. Plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. Or actually plus 0, plus 1, plus 2. So the bottom level representation could be like that. You choose one from the top, okay, and then add the one from the bottom. Okay, this would give you all representations possible. So you can see with the right hierarchy, provided that you can use your bottom components quite a lot, you could potentially represent more with less. You could represent a lot more things with just fewer kinds of representation if you just group them at the right level and you just add them in. Now, of course, you know, if you could condition things on the top, okay, because sometimes, you know, in real life situation, your octaves might be different. Like this particular octave on the left and this octave on the right, it might be different. Maybe this octave is a special octave. You need to plus a frequency of, I'm just giving you an example, like plus frequency of 10 hertz. And then this set of octaves here, you need to plus a frequency of 30 hertz. Maybe the piano is wrongly tuned or something. You need to represent things differently. What you can do is when you condition on your top level, your function when you condition your top level, okay, will give you the like plus 10 hertz, or plus 30 hertz plus X. Okay. X condition on top level. Yeah, so it will give you the like the amount of offset needed to represent the different things with a very flexible learnable function like that. So this is very, very powerful because you can then represent things that are different slightly. But if you have this very flexible function here, you may be able to still be able to use this hierarchy representation and reduce the amount of things that you need to represent. What's even better is this function could be learnable by the data. Yeah. So this idea of conditioning, mapping the, so if you look at the memory thing that I was talking about earlier, you have a top level vector like that, start position plus movement. You have a bottom level position plus movement, but this bottom position plus movement could be conditioned to become something else based on the top. So it becomes like, after you map, it becomes like that maybe. Yeah, so it's very versatile. You could use the top level to condition your bottom, and you can represent a different vector altogether. Yeah, which shows that like something like this hierarchy could be a very, very powerful way to represent a lot of things. Yeah, maybe I just pause it for a while. Anything you want to like add on or ask?
For this particular paper for Jukebox, right? What do they mean by encode 8 times? Is sampling rate, is it?
Yeah, I believe it's sampling rate because you see the coarse grain representation, their bars are fatter, which means that like one bar represents a greater time interval. I mean, if I'm interpreting this diagram correctly, this length here is the time interval of the audio.
I see. In a way, this is also, did they mention about like disentanglement? This is closely linked to that, I guess, because you don't, like you said, you don't exactly need to map up the entire wavelength for your song or your sound generation to actually represent it. You just need, like, for example, a very distinct portion to differentiate between the respective wavelength. So in this way, they're encoding at a separate sampling rate, what they call this.
The disentanglement is through abstraction. Like basically the more coarse grain signals get disentangled from the more fine grain signals.
Are you able to click or play us the reconstructed audio now?
Oh, I can try to find it online. You give me a while.
Nah, it's okay if it takes a while.
Yeah, give me a while. Let me try to find that paper. Yeah, let's see. That's my stop share. Yeah, it's an interesting experiment. Yeah, what's AI? Open AI. Let me just share with you this one so we can see whether we can find it together. So I picked Jukebox because like it looks like it's quite interesting. Okay, look at this. So this is how they did it. Okay, we can take a look together. Okay, because it's been a while since I took a look at their paper. So the raw audio is like this. So they compress it. Okay, using this. So it's true. So it's based on time interval. Okay, and then we see once they condition on lyrics. Okay, so they already get a different kind of output factors, which means that you can actually map the factor based on some conditioning factor. Over here, you condition on lyrics. Okay, so let's see whether we can listen to this. This is the original audio. Let me know if you can hear it.
Click it again.
I clicked on it already. Can you hear it? You can't hear it, is it?
Was that sound supposed to be a...
Let me share with you with sound. Okay, so let's share this whole thing with sound. Okay, let's hear it now. Can you hear it?
Oh yeah, we can hear it now. That's the song, original song.
Let's see the reconstructed. Maybe you start from the worst, I think. Then if you talk with the middle layer here, this is what happens. If we talk about the most fine-tuned layer, this one is here. Actually, this like most
I'm not a musical. I'm not an expert in the musical field, but it all sounds similar to me, you know.
Okay, you hear this. You hear this. Okay, then we look at this, the most coarse grain. You get the noise. There's a bit more noise here, and all this noise are like sort of removed after you put in this bottom level.
Oh, yeah, I see. So it's more muffled at the top layer, or the sampling rate of 128.
It's more high fidelity towards the bottom layer. So this actually similar to like residual vector quantization in the sense that you are doing the residual here. Like the residuals get passed down here. And the residual will then be interpreted by a different codebook, and so on and so on. So that you can represent something more complex, like, the piano keys. This bottom level could be the keys. This top middle part will be the octave, and the top part could be like different pianos. Yeah. And I mean, what's even interesting is they showed like this process here on the side. Thanks for asking me to show this. I think this, with just the train transformer condition of lyrics, you can already change the output. You can already change the top level representation, even without like conditioning on the middle layers. You just condition on the lyrics is enough to change it. Yeah, which makes sense, because like if you look at the top level, you hear the top level thing already has the lyrics, right? You look. So if you need to represent the lyrics here, you better change the color based on the lyrics. Yeah, or change the vector based on the lyrics. Okay, so yeah, let's go back to the slides. Now this jukebox thing is really quite interesting, because I think this is the okay, can you see my slides now?
Yeah, we're back at the slides.
Yeah, so this jukebox thing has shown me that this hierarchical abstraction actually works. Okay, their audio generator is not bad. And later on, I think I talked about VOL-E before. VOL-E builds on like also this kind of residual vector quantization to make the sound more high fidelity. And I believe all this residual vector quantization so on is a form of hierarchy, because you start with the most you start with the entire signal. Okay, you pick out like certain chunks. Okay, you pick out a certain vector and then you quantize it. The residual comes here, and then you quantize the residual, and then the residual comes here. Yeah. So this kind of way of doing hierarchy has already been shown to work. And this can actually be used in many different domains as well, not just audio. Just that in audio, people use it more because if we want to represent this bottom level frequency a lot, like you just want to use only this level here, you will need a lot of information to encode it. But if you do it by hierarchy, you can encode it in much less information, much fewer. So because when you talk about audio, you want to compress it as much as possible. Somehow, when you do hierarchical prediction or hierarchical generation, you compress it a lot, because you don't have to represent every single possibility at the bottom. You can just like take one possibility here plus this possibility plus this one here. You reduce your possibilities a lot by doing hierarchical representations. Okay, let's move on. So a very, very closely linked thing is residual vector quantization. I believe in Jukebox, they already did residual vector quantization. Okay, but residual vector quantization is like this. So as what I mentioned earlier, like for example, you have a vector like this. Okay, so at the first layer, maybe you have a vector like this. Okay, so at the first layer, you have this first quantizer. So your residual for your first layer may be something like that. So this is the residual. And then what you do is you find another vector most closely matched to this residual in your second layer. So in your second layer, maybe you quantize it like that. Or I use a different color. So over here, I just draw a vector because I'm quite lazy to write out the exact like vector embeddings, but I think you can get the idea. So in your second layer, you can represent something like that. And after you minus off the residual for the second layer might be something like that. An even smaller vector. Okay, even smaller like vector like that. So you keep doing this until you reach the end. So like you could have the first layer. This vector here is maybe vector 2. And then this layer at the bottom here, it could be like vector 3. I mean, based on the codebook. So you have different codebooks for different layers. Different codebooks for different layers. That's what you see in the Jukebox earlier. You can see that each layer has different codebooks as well. Like all these have different codebooks. It's not really shown here. This codebook here is not the same codebook for each layer. Each layer has a different codebook. So you can do this residual vector quantization to form hierarchies. And what I find this quite amazing is that you could use this kind of methods to form hierarchies over anything. As long as you can represent them as vectors, you can use maybe clustering methods to cluster the most common vectors for your first layer. And then you can if in the case of a piano, I already know that the most common thing in the piano is maybe the octave, because I hear that this octave gets repeated many, many times. So if I cluster my representational samples here, this one can become vector A, or I mean, this one can be vector 1. I call it V1. Vector 1 could be the center of this octave. V2 could be the center of this octave. And V3 could be the center of this octave here. So as long as your input is a vector representation, you could potentially already cluster, the most commonly found. Again, you need to know how many cluster centers are there. So if you know you give the cluster centers as 3 cluster centers, you could use k-means, clustering, in order to get where the cluster centers are. And then within the next layer here, you could then cluster the inputs based on the different levels here. So if we talk about from the center of the keyboard, you could have -3 all the way until 0 and all the way until +3. Yeah. Right? Correctly. Or -3.5, I guess. Yeah, because -3.5 to +3.5. And then here maybe it's +0.5. Yeah. So you could actually represent all your keys just by adding this first vector, and then you add this layer 2 vector. So maybe we call it layer 2 vectors. This is layer 1 vectors. Yeah. So I find this quite compelling because you could represent things in hierarchies just by doing clustering. And at each level, you take the quantized output. Okay, you find the residual here. You do k-means on this residual, you can get the next layer here. Yeah. The only problem with this process is it takes some time to quantize it. So I think this needs to be explored further, because there's a lot of things that could be done with residual vector quantization that could already be used to represent hierarchies. Okay, just by doing clustering, you can represent hierarchies already, because you take out the coarse grain component first, you take out this V1, V2, V3 in this layer 1, and then whatever you left with, you cluster again, you can form the more fine grain representations and so on. Yeah, so I like this idea a lot. And you can see that in the Jukebox that you saw earlier, they also use some form of residual vector quantization. One thing that I would like to say is that because we kind of say we want to condition on the top layer, we want to form this function here, function X condition on the top layer. Is this conditioning simply just adding? So this is something to think about, okay? Is condition, let me just write in a different color, all right? So later y'all feel free to chime in on this. Okay, is conditioning on the top layer similar to just doing vector addition? Okay, because right now, we are just doing vector addition due to the way we do residual vector quantization. We just add up the vectors together. So maybe at this bottom layer, you just add up the top layer vector, you add this up, and then you add up the bottom layer, and then out comes the final output here. So should we just do this vector addition?
When you say adding up, you mean concatenating or actually adding?
Just vector addition, 2 plus 3 becomes 5. It's not concatenating, it's a real addition.
I guess it depends on, because one thing to know, right, in order to ensure that your conditioning actually makes sense, is that there has to be some relationship between the top and middle layer. There's a reason, for example, a good benefit you were talking about this is that instead of considering entire problem space, if we can call it, if you're able to group it in such a way, you are simplifying the problem so that you're not feeding your model with too much require too much information to actually solve the problem. So if it's conditioned properly, you don't exactly need to approach it in just vector addition. There could be other ways you can handle because it's basically how to differentiate between the different partitions, right?
Yeah.
Like I think concatenating could work as well.
Yeah, but concatenating makes the representation like much more difficult to interpret near the end. Yeah, you probably need to just do some form of operation such that your final vector will remain the same size as your initial vector. If not,
maybe concatenating in the frequency domain or something.
Yeah, I think in terms of the hidden representation for each abstraction layer, it should still be about the same dimensionality, so that you can use the same kind of neurons for each layer. If not, each layer will have different kinds of neurons, which is not very probable in the brain. I mean, I'm talking about biology here, but it helps with the interpretation of the different layers as well if you have a fixed representational dimension.
I mean, from signal processing perspective, it's the same, right? You add in time domain is the same as you do concatenation in frequency domain.
Not concatenation. You are doing the convolution in the frequency domain.
It's, I think, convolution and multiplication. So you multiply in the time, you convolute in the time domain is equals to the multiplication in the frequency domain.
Yeah, correct. Yeah. So it's
no, but here my understanding is your different level in your hierarchy, they probably have the components of different frequency, right?
Yeah, correct. So the top level should be the more coarse-grained details.
Yeah, so in frequency domain, they are entirely separated. That's my understanding. So in that sense, you concatenate them.
Okay, I mean, there are different ways to interpret. But what I feel is that if we go into this vector addition, this vector addition is actually a bias. Because if you do a vector addition, there's no need to learn this function here. Because this function will just be the function will just be represented as x plus stop. So you don't have to learn this, which means that you free up this neural learning for other things. So if your use case could just deal with addition, then yes, good enough. But if your use case cannot deal with this addition, you might need to map it into a different kind of dimension and then perform this addition in a different dimension. Okay, so this actually has some similarity with the way we do transformer self-attention at different layers. Later, I'll touch upon this. I think transformers might actually be doing some form of hierarchical prediction already, just by the fact of their iterative structure.
Oh, sorry, I still have some question I want to clarify here. So this remind me of the volley we discussed last time.
Yeah.
Is it the similar idea or something?
Similar idea to volley. The hierarchical representation, similar idea to, I would say residual vector quantization is a way of doing hierarchical prediction.
Okay. But I don't understand. Something I don't understand is how does this save the memory? You don't have to store that much information. When you combine different levels together, isn't that just the original information content?
It's much different. So imagine your piano case, right? 21 keys, right? You have 3 octaves and 7 keys. So if you were to store in hierarchy, you just need to calculate you just need to store how many different representations. You just need to store 10 representations. Compared to if you don't have any hierarchy, you need to store 21 representations. Can you see that there's actually a polynomial decrease because you don't have to do the multiplication. Instead of doing multiplication, you are doing adding. So for example, if you have m times n times maybe p possibilities, this is if you have no hierarchy. But if you have a hierarchy, you just need to represent m plus p. Yeah, can you see that there's a huge decrease?
But I think this analogy assumes that within each hierarchy they have the same structure.
Correct. So I'm saying that if you don't have the same structure, okay, perhaps this vector addition may be may not apply, because if let's say your octave, the keys in the octave do not match exactly for each octave, you might need to map each octave differently. You need to plus 10 hertz or need to plus 35 hertz. So this function here cannot just be equals to x plus top. You need to do really a function, a mapping function here that's really conditioned on this top part. Yeah, so with that kind of vector conditioning, okay, you may be able to represent even though it's not a direct mapping. So you don't have to just do addition. You can do like, we could do a function space.
So
like
this is something need to be learned, right?
Times x, yeah, plus beta times top. You could do something like that, a weighted kind of thing. This needs to be learned, of course, yeah. It's either learned or it's given as heuristic.
And this is also in frequency domain, because I think in the piano key case, I can think of it as like in frequency domain.
Yeah, of course, you can represent a frequency domain also.
Okay.
Actually, you should represent a frequency domain because the keys are in different frequencies. You're right.
Okay.
You're representing a frequency domain for that.
Okay.
Yeah. So to answer this question, is conditioning on the top layer just doing vector addition? The answer is hopefully yes. Okay, because if it's like piano keys, you can do this. You save the learning of this function. Okay, but if you cannot learn, but if addition is not not the way to represent, you need to learn the mapping. And this is something that will incur some costs, but you have to learn this mapping in order to use the hierarchy. If not, your hierarchy cannot be used. Like in the case where some piano keys like are slightly higher, like plus 10 Hertz for this middle section, you cannot just apply this bottom left section and just copy and paste to the center because it doesn't work. You need to apply some offset. And so this mapping needs to be learned based on the particular situation that you see. Yeah, so hopefully, I mean, in most situations, you can just do an addition, but this may not be the case. So this may be why like residual vector quantization might just be one part of the solution. You might need these very flexible function operators in order to do like whatever I just talked about, which is like very flexible hierarchies. You know, earlier when we talked about this this part here, I thought about your next vector needs to be conditioned on your current state. Your next projected movement needs to be conditioned on the current state, as well as whatever is on the top. You need to condition on this. So, you know, you will need to learn this function, I believe. Yeah. So this is not a trivial problem, actually. And residual vector quantization might just be the very naive kind of version of this kind of mapping, because it just assumes that you just add the top layer. Yeah. So I know what I'm talking about right now is some ideas that I'm having right now. I believe over here, they don't really do a function mapping. They just do addition. Like they are probably doing, apart from the top layer conditional lyrics, okay, the bottom layers, they are all just doing addition, residual vector quantization, if I'm not mistaken. Okay, if I get this wrong, I will just update in the comments in the video, yeah. And I also update you on next session, yeah. So I think this is something quite interesting to think about, because you know, this might just be the way to represent hierarchy naturally, but you need to incur the cost of doing this k-means operation. I haven't thought of a way that you can do this quantization without doing this k-means. Because like k-means clustering, you don't need the labels, you see. You can just take the data and form the representations, which is good because no human annotated data is necessary to do this.
Sorry, one more comment. So basically what it is doing here is to learn more compact representation of the voice, right?
Yeah. So if you look at the jukebox, the top part here, this I remember from the paper. So the top part here is like, because they say music structure is similar for a large section of the song. So over here at the top, this is like the music structure. Then maybe these are like the special like segments. And then down here you have the more like voice, intonation, drums, you know, some special stuff towards the bottom. But at the top, if you're doing a rock song, your beat is generally the same. Boom, 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 boom. You know, that top part can really give you the beat. The bottom part, maybe some parts you don't have the sound. Some parts you have more sound. And this part here is like, maybe sometimes you purposely go off key, you know, that kind of thing to make the song sound unique. This part here could be at the bottom level. But in general, music structure is highly repeatable. And so the top part here, they encode a larger section like that. Because, I mean, for all you know, you could also encode it in the same chunks, right, as the bottom. You could encode in the same kind of like time.
Yeah, I agree on this, because I did a bit of music arrangement before. Yeah, so I understand what you're talking about.
Yeah, so in some sense, this hierarchical structure, they also did it with a greater time block here, because the assumption is that for music, the same music segment, okay, would contain largely the same themes. Okay, and so this is like maybe one section, the theme, and then you split into like sub-themes and then sub-themes and so on. Yeah, so this is like the way you do it. If you talk about this residual vector quantization at the bottom here, okay, you don't have to do like bigger blocks at the top. You can also all do the same kind of blocks, same width. It's just that in Jukebox, they do it special because they say music has this kind of structural framework, which I agree also, yeah. Okay, this is an interesting thing. Let's move on to images. Okay, any of you heard of this before? Feature pyramidal network or feature pyramid network? Okay, so the idea is like this, all right? CNN filters generally are scale variant. They are not scale invariant. Like if you zoom in the picture versus you zoom out, you might get a different prediction. Okay, so one way of like solving this is if you could do some form of hierarchical like learning, you take a large, okay, so this is the, like you can do, one way to do it is to just do it by different scales. You take an image like 16 by 16, and then you use it to do your CNN and you predict. Then you do max pooling or resizing, you do 8 by 8, and then 4 by 4, 2 by 2, you know, something like that. You could rescale the image at the beginning and then perform like your convolutional neural network to predict like maybe the class over here. So this is like one way to do it. Okay, but this way loses information because like the top part here, you zoom into 2 by 2, like imagine you take your image and then you zoom into 2 by 2, you will just get like maybe 4 squares here that doesn't mean anything because like this one is very dark, this one is like less dark and so on, but it doesn't give you any information at all. But at the bottom level here, this tells you too much information. So if you don't have the layers talk to each other like that, your prediction here is very, very limited. I mean, it'll be great to do like scale invariant kind of stuff because like if you zoom in or zoom out, surely one of these levels might capture the information. So that's possible. Another way to do it is to do this kind of thing like feature map. You just like, this is what we do in traditional CNNs. We just like, from the most coarse grain, we go into, sorry, the most fine grain detail, we do like max pooling, then max pooling, then max pooling, or use your filters, and you don't do the same padding. You just do like the valid padding. So your image will shrink as you go up. Okay, so you have image compression as you go up here, image compression. And then at the end, you just predict a class over here. So this is one way of doing it. This will be scale variant because like the initial scale matters a lot for your prediction because your filters are the same. Like your filters don't predict a zoom in image and so on. Okay, so one way of like solving this kind of issue of like scale variance is like you could do something like a feature pyramid where you can like at each level you try to predict something. At each level you predict something, and not just at each level here. This, instead of just being the original image like that, okay, you are using this new image, or rather this new representation generated by your first layer. You using your next representation generated by the earlier layer and so on. So in some sense, your representation is conditioned on the earlier layers. So the representation here, the abstract representation, is conditioned on earlier layers, which is quite cool because it means that you could extract out the more relevant stuff as you go up this layer. And you know, this abstraction way of doing it, if you use like filters or what, this is learnable. So this is learnable based on objective. If we were to look at this top part here, you know, this, can you tell me whether this is learnable or not? Is this learnable based on the objective? Anyone can tell me? Is this one learnable?
No.
So this is no, because this is already based on a fixed heuristic. So it's something like you know you want to resize it. So this is a fixed heuristic. But if you do something like this, condition on the earlier layers, so again we have this thing called like this fx condition on bottom. So it tells you like what is the kind of thing that, like you can learn this function f. Like this f could be like your filters, your CNN filters. Yeah. So this kind of way of doing this helps to align to the goal itself, because the goal will generate you the representations needed for the different layers. And then you could like predict, and then maybe you could concatenate a prediction and do an MLP later, or you could like do majority voting and so on. Okay, but this is not exactly the best as well, because what happens is that you get this kind of representation, but because this is still a compression objective, you just compress all the way to the bottom. Okay, but you don't really use this top level to condition on the bottom, because sometimes maybe, the way you interpret your image, like if let's say you are interpreting like an image as C, okay, then you could have like something as a boat, but if the image is on land, then maybe it's a tank. So you want to like, maybe a top level representation can tell you whether it's a sea or whether it's a land. You want to use this information that you get from the top. Okay, maybe over here tells you it's a sea. Then you want to condition, let's call this function G, Gx condition on top. So you want to condition whatever we have, this prediction, on whatever we learn from the top layers, because the top layers can give you the meta context. It can ground your bottom layers. And so your abstraction layer here can change based on the grounding. And then from there, this kind of grounding can give you this prediction here. So it's from bottom up, and then from top to the bottom. So just now we saw in the way we did the hierarchical quantization in the residual vector quantization. Okay, residual vector quantization is something like this. Actually, no, it's actually more like the first one, because you only predict once. Oh no, it's here. It's like residual vector quantization, because you quantize at each level of the vector. But we don't really have the case whereby you use the whatever you learn from the top vector, you use it to like condition all the way at to condition the bottom. So let's see whether we can draw some parallels with this. So like you see over here, you already quantize the stuff at the top. Okay, but because we are doing like something like residual vector quantization, you are still essentially doing something like this. Yeah, numbers part C. Okay, we don't really use the bottom level thing here to like predict the top. So like we don't really use this thing to like predict the top here. There's no two-way stuff. So if we do something two-way, then it'll be more like D, which is the feature permit network. So anyone can tell me like why in music we don't like condition the other way? Like why is the state of the art not two directional?
I guess it's because the lower sampling rate innately has more information about if you sample at a higher rate.
Yeah. So in this case, the most lowest context for the lowest fine grain details for music doesn't affect too much for the broad details. Okay, but over here is actually slightly different. Actually, the more we get up here, this is the more abstract. But for residual vector quantization, is the other way around. The more we go down the quantization, the more fine grain it is, the more detailed it is. So it's slightly different in terms of what we do. So for music, you don't have to go the other direction, because like conditioning on the top is enough. But for images, because this is the problem with images. You see, you don't really have like text telling you, okay, I want to do something for C, and then like I want to do something like a boat over here. You don't have something telling you at the top, unless you are doing like stable diffusion. You can condition on the sentence, but you don't really have this talking about this, like what to look out for by some oracle. You don't have that, so you have to like look at the most abstract view, and then you can use the abstract view to interpret the image at different levels. So this part here is just to get the different abstract views, and this part on the right here is to use it for prediction. So this part, feature permit network, quite interesting, because for images, we need to do that. We need to condition on different contexts, and then based on the different contexts, we interpret the image differently. Like sea become boat, land become tank, that kind of thing. Yeah, I really think this feature permit network is something like the feed-forward and the feedback connections in the brain, in some sense. That is sort of implicitly doing that. Because if you look at like the GLOM architecture, it's also similar. You go to the most top layer. This is the most abstract layer. And then once we use this signal to condition that on the bottom here, you use it to like give a better representation of like this level here. Yeah. So perhaps like what they do over here for GLOM, it might be useful. Okay, because it kind of looks like this, right? You see, over here we have the top layer. Over here we have the middle layer. But you see the difference here? There's no bottom layer. Okay, so GLOM tried to do everything in one. Okay, probably that's why it didn't do too well. So over here, they only have this top layer like that. The bottom layer only goes up once. Once you do the interpretation here, the interpretation is only based on the top and current levels. You don't do the bottom level for the interpretation. Yeah, so this is perhaps why GLOM didn't do too well. Maybe you need to cut out the bottom layer, or you need to do something like this feature pyramid network. This feature pyramid network is quite good, by the way. It's still used in YOLO V8. So there's something that they got it right, okay, in this feature pyramid network to extract out the things in this context and using this context to condition on the bottom layers. This is also used something similar is also used in UNet. Have you heard of UNet before? UNet is to predict like segments for different like objects. So the structure also looks like this. It looks like a U shape. So it looks something like a feature pyramid network. Yeah. So something like this, whereby you have more and more abstract representations, and you use the abstract representations to condition the next more fine-grained stuff. This applies for images well, because like for images, you have like some people, let's say the image is something like this. The image is some people here. Okay, I don't know how to draw people very well, but you have people here. And then maybe you have like a frisbee over here. So it's very hard to tell from the fine grain, okay, people are playing frisbee. But once you go into the context, like at the top, maybe you can talk about like game playing or like sports. Sports can be the highest level context. Then you could narrow down to frisbee. Then you can 2 people playing a frisbee. You see, as you get from the more macro to the more micro, if you condition on the top, you can get a more accurate representation of what this image should actually be, like that. And this is probably what this, a proxy of this is probably what is being done in feature pyramid network. And I find this quite incredible. Yeah, so we probably need to do more of this.
But what you denoted there, the concept. But when you actually go from high level to lower level, you're going to do something like upsampling, right?
Yes.
I mean, the model is going to do something like upsampling.
Correct.
That's definitely not trivial.
Yeah, I guess maybe the way it's implemented here might not be the best form, but I think the idea is there. The idea of conditioning on the top and the front layer is probably correct.
I also have a question on the figure C.
Okay,
so
yeah.
For the intermediate level, you want to do prediction, you still need to further down sample area. So yes. you still need to shrink it. So how is it different from the high level one?
You mean B, is it? How is it different from B?
C. How is it different from B? Yeah.
You have multiple levels
for each level
prediction. So like over here, this prediction signal may not be, this is the objective. But here, this prediction signal may not be the objective that you are predicting. Like it's just used to perform the context for this level here, which is used for this thing here. So it's an indirect prediction.
So it's predicting something.
It's predicting an intermediate. It's predicting an intermediate state, which is used for the upsampling later.
So it's some other class, some other.
It's I will call it a latent representation. It's like an intermediate representation of this model.
So how do you obtain the ground truth for that in advance?
This is something that has to depend on the prediction objective. So like if it's a classification objective, then the ground truth will be like backpropagated from the. So if this prediction is a classification objective, then this will be backpropagated from the ground truth. Oops, sorry. Let's. Yeah.
Then you are still using the same ground truth, right?
Yeah, using the same ground truth. Yeah.
Then it's the same thing, right? Unless you directly go from there, directly goes to the output. Otherwise, if you still have the intermediate, then it feels the same as you go upwards.
Yeah, so I think what yeah, I guess in this case the classification objective for images, unfortunately, like we can't really do like next token prediction for image, because like I mean next token prediction means you generate the entire set of pixels for the next state, yeah, which can be quite lossy for images. Over here, the classification objective, you're right. I mean, it may not give you the right intermediate it might not give you the right intermediate representations here.
I guess it's just the figure is not clear. How is it really done? Yeah, so I'm quite
but you're right, it's upsampling here. Yeah. So I would say that we just use this figure as a proxy for trying to understand how to interpret images.
Yeah, it's
because
a bit too high level, I think.
Yeah, I actually may not agree fully with like what they do here, but this diagram here, I agree with it. The high level concept, I agree with it.
Okay. One more comment is, I think for D, right, you probably can do the same for music as well, because to me it makes sense to you come up with the. I mean, that's actually I think most of the conversation, how they do a conversation. You come up with the motif first, then you come up with the melody first, then you come up with the you harmonize the melody, including then you can come up with the bass line. So actually, it's a top-down approach.
So this is
to me,
melody,
it makes sense.
Yeah.
So the high level is motif, melody, your then your different harmony part, maybe counter melody. Then your bottom level is your bass line. So it does make sense to go from top to down level. So maybe.
But however,
just they haven't tried it yet.
Why do we need to do this part? Because like when we want to talk about music, normally you want to say, I want to do a rock song. Then you can start from the top already. You don't have to do from the bottom for music.
No, because I thought just now you mentioned for the quantization or something, like you go from low level to high level.
Yeah, correct. Maybe you quantize the motif first, then you quantize the melody, then you quantize the drums.
So I'm saying I think both way works, right?
Yeah, I think the difference between image and audio is that for audio, you already know in advance like what style you want to do already. But for image,
that's why
for image wise, you may not know the style straight away. You need to like infer the style from the diagram, and the style is usually like the last thing to be inferred because it's the most high level. So perhaps that's why in images you need to do it like this way first. You need.
I'm not saying you can't do it for images. I'm saying it makes sense to do it even for music.
Okay, I need to think about this. Yeah. Okay, so let's move on. I think I spent a bit too much time. So today might need to drag about half an hour more. Are you okay if we end at 6? Yeah. Okay, so this is hierarchical JEPA. So this is Yan LeCun. So his JEPA architecture is basically you want to predict in some latent space. And what they're doing here is in hierarchical JEPA, you're predicting a meta level action here, given some objective, and this objective is to minimize loss or minimize costs. All right, and this cost is like an intrinsic cost. Okay, that's determined by the agent. Okay, so in like my goal-directed approach, this objective would be to attain the goal. Okay, so I think it's similar. It's just that like one is goal, one is cost. So it depends whether you use value functions or you want to use goal-directed learning. I'm more of a goal-directed learning person. So you have a meta level action, and this action here is then conditioned as the goal here. This will be like the goal state. So the goal state for the bottom condition on the top actions. So like if you and then you have the same thing at the bottom, so you repeat the same architecture. So like for example here, this is the action walk. Then the bottom actions here could be like left leg move, right leg move, and so on. So the action over here could be run. And then the bottom level action is the same thing, left leg move, right leg move. So there's a form of reuse here. Like your action space could be reusable. And if you reuse the same actions, you could like form more and more complex plans towards the top level just by using reuse. And over here, unfortunately, Yan LeCun's architecture is still using cost, okay, using some form of value functions, which I propose to do away altogether and just go towards like attaining this goal here. So again, we have to see like whether or not this works. Okay. And but I agree with the fact that you do this kind of hierarchical goal setting. In fact, I believe the neurons in the brain, right? The output of each neuron, according to Jeff Hawkins, is always a motor output. And the thing is, the top level neurons and the bottom level neurons should not be the same, should not be different in terms of structure. So the top level neurons, the motor output here, could very well signify the goal for the lower levels. And at the most bottom level, these neurons could be go directly to motor, to muscles. Okay. But at the top level here, these neurons give the goals for bottom levels. Yeah, so there's some form of hierarchical representation of like the action space here, a hierarchical goal setting here using hierarchical JEPA-like architectures. So again, if you think about this, this actually has parallels with residual vector quantization. Okay, why do I say so? This intermediate goal here is like the first vector you quantize. So you have an RVQ as your first intermediate vector. As you go and break down into the sub actions here, okay, you are actually like doing what do I call it? Actually, it's something different because like you don't really do the residual here. You are trying to attain. Yeah, so this one is more like attain the act. So the residual part probably comes like here. Like if I were to think about it, in the residual part is here. Because the residual will then give you the next section of what you need to do to accomplish your goal. But at the bottom here is more like you are trying to piece together so given this objective, so you are also doing residual vector quantization here. So actually the RVQ is done here. The residual vector quantization is done in the temporal space. You're trying to do residual vector quantization such that you attain the goal that was set by the higher level. Does that make sense? Actually, this is the what I just talking about. I just thought of it. Yeah, seems like it could be the way to do it. I mean, if you have a fixed goal target here, and your actions just help to attain this goal, I mean that kind of works. Okay, so I have to think more about this. Yeah, so this I just leave it here. Okay, for digestion. When I think of something more concrete, I'll talk about it again. Yeah. Okay, anything so far before I move on to the next slide? Yeah, I'm trying to link everything together because like all these things are all interesting ideas used in different domains. There must be something common that we can use for everything because memory works for all domains. It doesn't just do audio, visual. The same architecture must work for all kinds of domains. Right, even reinforcement learning. Yeah. Okay, so another thing that I like to talk about is like hierarchical action prediction. This is in the case of like this thing called generative agents, whereby 25 agents in a sandbox interact with one another. And one thing that sparked my interest here is how they actually prompted the actions of each agent. They actually started with the broad action and then prompted to the specific actions. Like for example, they will ask the agent, where will you want to go? So they ask the agent, where do you want to go? Okay, then maybe the agent say library. And they were like, where in library do you want to go? So you bookshelf A, you know. So this one is they call it pass the JSON tree from macro to micro. So this macro to micro action prediction is done using text. And in some sense, this is more like telling you, like, if you infer this as the activity, like if you look at the hierarchical JEPA earlier, this one could be like you are doing the activity run. Okay, and then what you want to do to attain it, left leg move, right leg move. You know, something similar. So there's a hierarchy based on the action chunking here. And over here, this hierarchy is to go from more coarse grain to more fine grain. So I guess in some sense, you could also think of it as you go down here. Okay, this could be something like a residual vector quantization here, because you are going down the hierarchy to tell you like more and more fine-grained actions. Okay, So of course, whatever I'm just talking about right now over here, still thinking about it. But it does seem that there's some parallels in the action prediction and whatever we talked about earlier in the residual vector quantization, hierarchical JEPA. Hierarchical JEPA, the RVQ is done like here. So yeah, there's a lot of I do think this vector quantization thing helps a lot. But just using native RVQ as we talked about earlier, RVQ just assumes that fx condition on like top equals to x plus top. It just assumes this. So maybe we need to learn a differentiable function. Maybe need to learn. Yeah. So anyway, the thing is, this is done in the vector embedding space. You could actually prompt using text, okay, to get from most macro to most micro. Most macro to from macro to micro. This is something quite cool because you don't even need RVQ anymore for this. You can just condition on the earlier prompts, earlier context, just in the text space alone. You can actually do something similar to RVQ, okay, and you can get more and more specific details. I like this idea a lot. Okay, so whatever we talked about like this RVQ earlier, maybe this is done using like in domains where text may not be the best way to interpret things. You need to use embedding space. This kind of thing you should use for when text is your appropriate embedding space. You can use text to condition the macro actions and then you get the more micro actions. Then you don't have to do k-means anymore. You can just use text as a way to condition the future generated outputs. Okay, so this is something for fun that I did. Okay, so this is called sequential prompting. So like I tried to get ChatGPT to give me an activity planner. And then I say that, okay, I want you to plan me this. These are the objectives that I want to do. Okay, with some constraints. And then what I told ChatGPT to do is give me an overview of the plan for the day. Okay, and then based on this overview, give me the breakdown of the plan, highlighting whatever special requirements or preparations. So let's see the output for this. So like you need to buy bread, 2-hour lecture, breakfast, lunch, dinner, 1-hour game session, 3 hours group discussion. So we look over here. Not bad. You see, with the broad plan, it gives me the day's program with already like the 2-hour, 3-hour blocks already planned for. So in terms of planning, this is, I believe, how humans plan as well. We don't plan like, oh, this minute, wow, what I'm going to do this minute, what I'm going to do next minute. No, we don't think like that. We think, okay, in the morning, I'm going to do some research. In the afternoon, I'm going to play some games. Something like that. Yeah, we think of broad plans. Then from this broad plans, we can narrow it and then we can think, okay, what am I going to do in each 5-minute block maybe? Or in this block, like for example, in this wake up block, what am I going to do? So you can see the detailed generation is like, what am I going to do in this? I'm going to like set an alarm. I'm going to, do this kind of thing, nutrition breakfast and so on, gather materials. So you condition on the broad plan to generate the more detailed plans. So again, you can see this is the idea of macro to micro. And this all can be done using text alone. So text embeddings, or rather using ChatGPT or LLMs, can give you already the hierarchical structure from macro to micro. In terms of like condition on the macro plan, give me the micro details. Or you can also ask ChatGPT to give you 5-minute time blocks. That will work also. And also that's what they did for that's what they did for generative agents also. They asked the agents to plan the day. They also did in like 5 minutes time blocks. So let's see what happens, okay? If we had omitted the broad step, okay, we omit this one and we just ask ChatGPT to give me, so what I do is I just delete this one. I just ask ChatGPT to give me the detailed breakdown directly. Let's see what happens. And this is what happens. Okay. Yeah, this is what happens. So in this case, it looks largely the same, but you can see, oh, did I miss out one slide? Oh yeah, I missed out that slide, but let's see whether I can show you that slide. Oh, I must have forgotten to put it in. Okay, let's see. Okay, but you can just take my word for it that if you ask it to just do the detailed plan alone, all right, it does not give you like that detailed an answer. Okay, it gives you, like for example, it will keep asking you to eat bread. Like for the breakfast, ask you to eat bread, lunch, ask you to eat bread, and so on. So something like that. Yeah, because it's been like conditioned on this bread here. But if you were to follow this plan over here, okay, the lunch part, they may not give you like stuff like eat bread, you know. So it's more conditioned and more consistent. If you ask it to generate the broad plan first, then get the more micro plans, because the micro plans can be conditioned on this broad plan. So this is something that you could do for GPT to get this kind of hierarchical generation. This is what Terry was talking about, action space, right? So in the learning fast and slow, this is the environment. You can move up, down, left, right. So if we move the environment, like we keep going right here, down, you need a sequence of actions. Like for the planning, you need a sequence of actions to reach goal. And if your environment size is huge, okay, I realize that the memory retrieval part or the memory planning part takes very long, okay, to get a sequence of actions to reach the goal. Okay, so what could be done, all right? One way of doing this is that instead of like doing every single time step moving like that, your goal could be like you just move all the way until like your macro action could be like something like this. You can move to certain areas, and then you can have macro actions that cover like more of the action space. Okay, and this is one of the things that Hierarchical RL is doing. So there's something like options. So, I mean, you can just Google it. So I just learned about it today. So there's something like options where you can like, instead of going from like square to square, you could go from like, for example, you could learn like which parts of the grid are more important. Yeah, you could learn like how to go from here to here. So if you can learn like how to get to the center over here already, you essentially like sort of break down your problem into chunks of actions. So like the first chunk of action could be like go to the center, the second chunk from the center to the door. So it already helps you to break down your problem space into like decomposable parts. Right? Another way to do hierarchical representation is perhaps just do like sticky actions. Instead of just doing like one action, you can do two actions, you can do three actions. Haven't really thought about how to represent this. Don't even know whether you can do like residual vector quantization on the action space to get your hierarchy. But yeah, this is something I'm looking into. If we can have a more broad-based goal, okay? Like instead of just going to the goal, you could like go to the intersection between the doors or intersection between the walls. You could potentially, you know, solve the environment using two steps. So this step one and this step two, which means that if you do like planning, you may only need to plan like two different plans. One plan to the hole, one plan to the door. And then like condition on this plan number one, you have fewer actions to reach this sub goal. Yeah, so if we are able to split the problem into goals and sub goals, which is not an easy problem, by the way. If you can split into goals and sub goals using stuff like options or using stuff like, you know, just by using the structure of the world to give you the decomposition, which is an open problem right now. Yeah, if you could do something like that, you actually need fewer moves in order to reach the goal, because you could just reach the sub goal first, and reach another sub goal and so on. Right? Like, you know, if you were to do something like play a game of chess, you know, it'll be easier for you to plan in terms of, okay, I want to capture the queen first, then I capture the rook, something like that. So you can focus your efforts on just like capturing the queen rather than, oh, I want to win the game. So if you can break your plan into sub goals, it's much easier to plan that way. So again, that is something similar to what was done here. You first gave you your sub goals. Your sub goals are chunks of the day, and then you go into more detailed like planning. Is what am I going to do in this chunk? Very, very similar idea. Doing hierarchical kind of planning. You do the more macro part first, then you do the more micro part. Any questions so far before I move on to one of my last few slides?
One thing I would say is that it's very hard to say or to determine the sub goals, you see, because the sub goal might change. Like you're showing a maze, right? What is to say that, let's say the environment change and that sub goal is no longer an actual goal you should be heading to. Now it's a blacked out wall. In that case, the solution will never resolve, you see, because the algorithm will always try to find the blocked off wall, but the agent cannot access that particular block.
True. So this is a difficult problem to solve.
No, but I thought you mentioned before the planning is not done in the pixel space, right? So in this case, the intermediate goal is simply to pass through the wall.
Right. No, but what Dylan is saying is that what if there's no wall to pass through? What if this thing is not valid? Like what if the environment is something like this? Like there's many different walls, or like it could be like something like a maze over here. Yeah. How do you know that this is the sub goal and this is the sub goal? You know, like this is something that is a difficult problem to solve, because in order to find out how to factor your environment into sub goals, you need to understand the environment.
True.
Yeah, so this is a difficult problem. In fact, this actually, I don't have the slide here, but if you look at SayCan, what they do is like, I want a drink. So you can ask the LLM to give you like, first, find the drink. Second, pick up the drink. Third, move to you. Fourth, pass the drink to you. Fifth, done. So SayCan uses like, because the action spaces here are kind of simple to do. It's like move, pass, pick, pass, pick, pass, pick, pass. You can actually use few shot prompting of LLMs. You generate sequences of sub goals, and then these sub goals can then be done using the traditional like there's some policy that can be conditioned on some text. You can use this thing to condition the robot to move stuff. So one way of doing sub goals is if the environment can be represented using semantic means, like in this case, move and find the drink, pick up the drink, something like that. If it can be prompted using few shot prompting, you can easily use it to form the sub goals for that particular environment. Okay, but again, you know, you need to come out with the few shot prompting. You need some few shot prompting. Who gives this ground truth? Right now, the human gives it, but you know, if in an arbitrary environment, who gives you the sub goals? How do you get your sub goals? And that's a difficult problem that I haven't really thought about. Yeah, I haven't really solved it yet.
I can see your motivation. As in recent time, because of our language models, you can scale it to so much data, then they create this chain of thought prompting, right? That's the entire your goal of this chain of thoughts for the sub goals. In traditional neural network, people have explored similar effects. If like it's actually just local error signals, but then again, you have to select right or suitable local error signals.
Yeah, who gives the selection of these local errors? Is it automatic or is it a human engineer?
Yeah, that's true. In some papers, like they specifically design those local errors, like for example, maybe based on local errors that the variance of the layer should be constrained, or so all this various constraint that is still human determined. Then they try to allow the model to learn this the appropriate weights based on those local errors that combined with, let's say, a global error, you are able to achieve, like for example, reach your destination at the end.
Yeah, so I guess if the problem itself can be disentangled using scale, like for example, navigation, you can start by country, then go by state, then go by like neighborhood, then go by roads, you know, you can do by scale, then that will be a very natural way to do the hierarchy. Yeah, but in a problem like this maze here, like the scale is not very clear cut, you see. Probably one thing that could be done, I just thought of something. Some people have done like analysis based on trajectories, and then you see which like square is the most commonly visited, you see, like then this can be like the choke point and this can be the sub goal. Okay, but the problem with this in my fast and slow environment in this grid world is that the start and end state keeps changing. Okay, but over here, because the environment is the same, I mean, I guess you could say that you would keep passing through this square, and then this square could be the most frequently passed by square, and this could be a potential sub goal. I guess this is a potential choke point that you can like use it to condition as a sub goal. Who knows? I mean, people have also found that just using a random sub goal might even help the agent already, like just learning a random sub goal. So Yeah, there's some stuff that needs to be thought of for this, like how to get this subgoal representation.
In your setting, can the agent see the entire map or only the surrounding, the adjacent?
Setting the agent is blind, but I'm considering doing another experiment where the agent can see like the neighboring squares.
Blind as in it can only see its current state, or it can't see anything.
It can only see its current state, and it can.
Then how do you even plan if you can't even see, like at the beginning you can't even see the wall, right?
Yeah,
there's no way to plan. Then like I would argue there's no way to plan. It's not possible.
You can use the memory to plan.
So if I recall, what Choming did was, you can still plan, but you have to make some assumptions. You see, you're right that if you completely don't have any information, you are just randomly like brushing across your neighbors and hoping that you reach. But let's say if you have a bias like a compass in Choming's case, if you think about it as a Manhattan distance, you don't know how the environment looks like, but you know what your goal is. Like, for example, let's say I want a drink. The goal is that there's a drink in my hand, I can drink it, right? So the agent is able to see the door, as in he knows where the door is, but he just doesn't know the right path to get to the door. So in Manhattan distance, you assume that if you're getting closer in terms of the distance wise, you assume that will be a better sub-goal. So you're right that at the start, if you have no information, you're just randomly walking, random search. But if your sub-goal, after multiple iterations of random search, your sub-goal is getting closer to the door, you say that you are getting a better solution.
Okay, I see. So the agent does know where is the location of the door.
Yeah, you have the goal in mind, so you can move towards the goal.
Then I will argue like, just frame it as a search problem. Why frame it as a decision-making problem?
But what if decision-making is also sort of like a search?
Oh, I mean search in the sense that you can think of it as not to search the sequence of action. Okay, never mind. I think because in your setting, the environment is deterministic, right? So it's kind of the same.
It does change after a while. I mean, like 50.
Oh, no. I mean your transition probability.
Transition is deterministic.
Then it's exactly a search problem. Just use some search problem, like some algorithm, A-star search or whatever, like some heuristics.
Yeah, potentially you could reframe as a search problem. Yeah, but it's a difficult search problem because the start and end state keeps changing, which means you need to learn the structure of the environment if you want to search it well.
You don't really need to learn an entire. I can send you a video after this. I just watched it. I think yesterday. So
sure.
You don't really need to learn the entire thing. You can just follow some heuristic which guarantees you to find.
Oh, the left, follow the wall on the left, is it that kind of heuristic?
No. Because left, then what if you have a wall not connected to the boundary? Then you will go into a loop, right? It's not that simple, but it has been done.
Wall finding, wall following heuristic, right? Is that something?
No. I think it's called ring flooding or something.
Interesting. Yeah, you can let me know. So one thing about like the problem with action prediction is that we don't really know like how this action prediction, rather how this hierarchy is naturally formed. So I think this is a huge problem. Maybe for audio we can do quantization, but like for actions, can you really quantize your actions by hierarchy? So yeah.
If your action is just the action of orientation in the maze, then you do know, like you greatly know what is the shortest path to take. If there is no obstacles, then you modify this prior based on your experiences. What if you hit the wall, you change a bit, something like that. But I think in more generally speaking, if it's like a more general decision-making problem, how do you find the analogous so-called shortest path towards that goal, right?
Yeah, I'm still thinking about it. Yeah, but I mean, if as what we discussed, if the problem naturally breaks down into hierarchies, you can naturally form actions based on the hierarchies, like country level, state level, neighborhood levels, road level. Yeah, but for this one, it doesn't really break down that naturally unless you group by walls here. So this one needs to be thought about, like, how do we break down this hierarchy? Who gives the hierarchy? Like, you see few short prompting for the hierarchy in SayCan. Who gives this hierarchy? Can you learn it? Or must it be external, some hyperparameter, some fixed thing that you already use it? So this thing, I think we can discuss further because I don't have the answer for this. Still thinking about this. Yeah, but anyway, this is, I think, one of the last few slides. This is talking about how I use like hierarchies, okay, in order to like do something like the ARC challenge. So I tested this, it kind of works for some of them. It works for 3 out of the like 5 or 6 problems I've tested. Over here, ARC challenge is like you have an input image and you want to predict an output image, okay, and you don't have the rules. You need to infer the rules from this input to output. So one thing I asked like the LLM to do is I give this in JSON format, and then I asked the LLM, which is GPT-4, to give it like a broad intent. What's the broad intent? So the broad intent for this maybe is to reduce input to a smaller size. And then what I'm thinking is that you can reference past memories of like something similar to this JSON. You can reference past intents, and then you can like refine this broad intent, because a lot of the problems in ARC might have the same broad intent, like to reduce the grid. Then you can potentially like refine this broad intent. And then secondly, you can then condition to generate the detailed steps. So the steps could be like remove every other square. Again, you can reference from memory what are the possible approaches that are used to reduce the grid. Okay, and then you can choose the one that is most likely usable for this case. And then you just need to perform these detailed steps on the test input to get the answer. So there's 2 levels of abstraction here. The broad intent to guide the search towards this path that is most promising. And the detailed steps will then give you the more like specific steps to do. So the problem is if you were to do directly the detailed steps, you might be lost. Okay, you might not get the right conditioning. So by conditioning on broad intent, it helps to narrow the search space. Something like, you know, the action abstraction we are talking about. I guess if you could ask GPT, you know, what is the broad intent to get from here to here? Then maybe it can tell you the broad intent is to go to the door, passing through the hole in the wall, you know, something like that. This could actually form like the hierarchy, you know, if you could do like broad intent detailed steps. Again, I'm still thinking how to apply this for RL, but at least for this kind of works. Okay, and we can even get a few possible detailed steps and try out all of them. So you could generate a lot of possibilities and test them out. So this is something that I quite like about large language models, because it's stochastic. You can get different outputs for the same input. So this is a curse as well as a benefit. So in terms of like idea generation, LLMs are actually quite useful. So in this case, we want to generate many possible solutions. You can use LLMs to do that. Yeah, so this is my idea. I'm still testing it out. If it works, I'll let you know again. Yeah. So this is something interesting. So I'd like to just end on this slide. So this slide basically asks the question, can the transformer architecture perform this hierarchical generation that we are talking about? Can it condition on the broad level intents? Okay, and then conditioning on that, interpret the tokens in a certain way. For example, you know, like Sam went to the bank to draw money versus like Susan went to the riverbank. No, in both cases, the word bank needs to be interpreted differently, right? Because you need to interpret it in terms of your neighbors. But can we do such that like you can have some form of context whereby you already know that this is like a finance case, and over here you could have something like geography. So maybe you have a broad level context. Okay, so for example, if we put like the broad level context here, like maybe geography, can we use this broad level context to condition on the earlier cases, okay, in order to change the embeddings? Okay, so it turns out that it may be possible. Okay, because like in order to do all this, you will need something like the feature pyramid network, right? You will need to, from the input domain, you need to get more and more abstract. Okay, and then you go to the abstract space. over here. And then what you need to do, you need to have some feedback connections to go from the abstract space to condition on your input again. So it's like this. From abstract space, you go down here. So you condition your inputs by the abstract space. So I've been thinking, you know, I also asked Dylan, like whether we can use like graph neural networks to do something like that to kind of simulate the feedback connections that the brain has. Okay, because the feedback connections might be the conditioning from the top layers. I was toying with this idea, like, can you condition this top level inputs? So then when the transformers came out, I realized that just by prompting different prompts, like for example, you have this context here, and then you have your prompt over here, like for example, do the opposite. John went to sleep. Yeah, so because of that, like John went to sleep can be John became awake because of just this context, do the opposite. So this thing here could be like the abstract space, or this could be the abstract space. And somehow transformers, because you can condition on some context, it can interpret whatever you write after based on that context. It seems to be able to do this kind of conditioning by the meta levels. So I've been thinking, where in the transformer architecture could this be possibly happening? So, because if we just talk about just feed forward all the way from the bottom to the top, we just talk about feed forward, you know, it kind of just looks like it's doing this, right? It doesn't exactly like condition on the earlier layers. So, okay, let's assume that this part here is done in this part here. You get to geography. So for example, like Susan went to the river bank. So the input could be like here. How would I know this bank represents the river? How would I know that? Okay, so this is where escape connections come in. So whatever I'm talking to you is just my intuition. I haven't tested it out. At every layer of this feed-forward connection, I'm just using these memorizing transformers because, you know, over here it's a bit hard to go from token level because they don't show the tokens. But this, they show the tokens. So I'm just using this. There's this feed-forward connection at every layer. Sorry, there's this residual connection. It may be the case that the word bank, okay, gets propagated all the way up here, unchanged, okay? Or rather, it's changed based on like layer norm and so on. But the idea is the word bank more or less retains its original meaning at the top layer. So it could be the case that we have an output at one of the top few layers. The token representation of bank is largely unchanged, but we have this meaning of geography somewhere in the earlier tokens, okay? So we can, in the same layer, condition the bank on the word geography, or on the meaning of the word geography, and then you can update bank towards the geography. So this is one way I think the transformers might be doing hierarchical generation, although not explicit in the architecture because there's no feedback connection. Yeah, am I still here, by the way? Hi, just to check, am I still?
Yes, yes.
Yeah, okay, so one thing I was thinking of is that the residual connection might just be giving like the tokens a way to like go up the abstraction space. And so like the token bank might be able to be conditioned by the top level like that. Okay, because the original bank itself walks all the way up using the escape connection all the way to this layer, which can then be conditioned on this meta level concept. So that is one interpretation I have, that like, why can this kind of like context and prompt work? Because you need to have some form of context semantic space to do the opposite of this is not very easy, you know, it's quite difficult, but somehow transformers can do this. Yeah, they are able to interpret this message and are able to do the mapping to this stuff here, which is not easy. So perhaps like this idea of conditioning on the meta context could be due to the escape connection. Some of the inputs can go up, and then as you process hierarchically these inputs, this can be the more meta level concepts, and then this can form in the same layer here. So this layer here could be like meta concept and like maybe original tokens. Yeah, so you could influence the original tokens based on the context just by doing that. Again, this is my own view. I mean, I think the multi-head helps you to do multiple kinds of conditioning. And another interesting thing is that this thing here, as we go into this is the K, V, and Q, key value query. The transformer architecture actually in the key value query, they actually have a linear layer. So this linear layer could be doing a mapping. So earlier we have this function X given like top. So maybe this mapping is done by linear layer. Like the linear layer might be already giving you the way of doing the mapping, the condition at the top level. You need to map into the right space in order to do the conditioning. So yeah, that's something that I was thinking about. Yeah. Okay, yeah, I think I exceeded the time already. Yeah. Anything on this slide? If not, I think we can end soon. So have you thought of this in this manner before, or is this new to you?
What thing?
Like using the residual connections in order to do some form of conditioning by the top layer.
I thought it just because different multi-headed attention, different attention give you different context, right? That's my understanding.
Yeah, I mean that could be possible also, but then it cannot really explain like do the opposite. But
sorry, can you elaborate a bit? What's that do opposite about? I didn't catch that part.
Say again.
What about the do opposite part?
Oh no, I'm just saying that you could condition maybe the prompt on a certain context, do the opposite. And somehow the transformer is able to interpret the embedding space of the next part of the prompt according to your context. So this is something that is not easy to be done just by doing this token correction just by in a single layer. You need to have some form of conditioning based on a meta layer like this, condition on the lower levels. Something like this would be a more natural way to interpret this. And the transformer, if it doesn't have feedback connections. So I'm thinking the feedback connection comes because of the skip connection. It allows the original tokens to go up the layers unchanged, or at least change only by layer norm, which is applied uniformly.
So what does that mean in this context? What does do opposite? John went to sleep. So what's the opposite of that?
John woke up.
Oh. I don't know. I don't know.
Yeah, if not, how do we explain that? Just by conditioning on some context, the transformer is able to change its behavior so rapidly. Okay, yeah, just think about it. I think this one is no obvious solution. This is just some intuition that I have for. So transformers might already be doing the kind of hierarchical generation that we want, to do this kind of flexible mapping. I think it might all be already in the architecture itself. Okay, so yeah, let's just quickly go through this in maybe 5 minutes or what. So yeah, the first thing is, should we use hierarchical generation? I think we all agree we should. This part maybe is open to interpretation. You all think the brain is more hierarchical or more flat in terms of hierarchy? Jeff Hawkins says maybe the visual cortex only has 2 layers, the micro and the macro. Yeah, but CNNs, we stack up the layers. So you all think hierarchy is innate in the brain or is not?
Not sure the physical structure, but in terms of our mental state, to understanding the role, I do believe it's a multi-layer hierarchical structure.
Yeah, I also do
physical structure, I'm not sure.
At least for the concept interpretation, I do believe we go up the hierarchy. There's many different layers of hierarchies that we can imagine it to be, in a room, in a house, in the neighborhood. I believe that's very natural for concept representation. Okay, so next, how do we get...
I'm not a medical expert as well, but I guess one way we can support maybe the brain is hierarchical in nature is that we do have information that components of the brain are specialized in a particular task, right? But at the end of the day, when a decision is to be made, it has to go somewhere, right? So maybe the specialized components of the brain process particular information. Once you get that specialized information, those information have to go to somewhere. we can think of it as a hierarchy in that sense.
Yeah, so the iterative processing of the information is a hierarchy. Is that correct?
Yeah, to a degree. As in, I have no information. I just know, like, for example, Cortex is processing in this way, and so maybe the LOBA is processing a certain component, but I'm not too sure about how is that actually hierarchical.
That's true. Yeah. So I do think hierarchical generation is the way forward because it can do a lot of things like represent more with less, and it might be able to lead to a more like macro level planning before micro level planning. This helps a lot with like reinforcement learning as well. So the next question is, how do we get these abstractions? So one way is like to chunk actions together. Like, for example, you see like left, 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 right. You know, you could chunk to like mega left and right. So you could just like do the action. One time you can do 3 actions. So I think both help, but I haven't quite figured out like how exactly do you arbitrarily do it, because you know, you could just arbitrarily chunk frequent actions together, but it may not work that well because you know, this left might just be only for the left side of the board, may not work for the right side of the board, and so on. You need some conditional chunking, which is very difficult to do. And right now, chunking is done mainly by frequency. Vector quantization can learn from the data because you can cluster it. So maybe this could help. If you can make your actions into some vector representation, you might be able to do vector quantization on sets of actions. I mean, vector quantization is used already in audio. So that might be one of the things that we could do. Any comments on that? Like this question? Okay, if not, I think this one needs some thought because I haven't quite figured out how to do this yet. In fact, a lot of people haven't quite figured out this. But you know, if we can do something,
I think maybe in general we have 2 approaches, either top down or bottom up. Yeah.
So
top down, then you go to the level where you can execute it. Then yeah, I don't know.
Yeah, I mean, another way to do this is to use a text to do it. Like use text, and then you can ask the LLM broad plan, detailed plan. You know, you can do something like that as well. So you can let the LLM give you the, you can ask it to give LLMs to give goals, sub goals. You know, like Auto GPT, you can split the, or maybe AGI, you can split the problem into sub goals. So maybe text could already do this hierarchical abstraction for like very meta level concepts. Yeah, but for like lower level action spaces like movement or this, I think some form of vectorization needs to be done.
But I think the question is more of how even LM able to come up with a legitimate hierarchical abstraction. So you mentioned detailed plan. So you remind me of, so if I was talking about bottom up, right? Then that means the bottom up is you start from the unit, the atomic action, you know you have to do it. It must be done. Then you from there you go up. Then the top down is you know that there's a general goal, high level goal that must be done. Then you go from there downwards. So yeah, you anchor yourself at some place first, then you go from there or something.
I think planning is done from top down actually. Like you need to do the macro level plan first, then you do the details. Like you need to anchor on the macro plan. Like I need to say, oh, I want to go to school today. Then from there you can plan, oh, what bus should I take? Or what should I do to get to my car and so on. Yeah, so I do think the anchoring is very important because it limits what you generate. It limits the solution space.
But in the maze problem, if you know like there's only one bottleneck, you have to go from there. Then that's some action you have to take, even regardless of what high level goal you have, right?
Correct. So the way we do the sub goals, but I mean, if it's something semantic related, like for example, like what should I do to get from point A to point B, then you know like how the structure of the world is. You could do like broad level actions, like from point A I go to point C, then point B. That is natural if you can split it by, if the environment allows for it. But for the maze, The maze, everything is micro, you see. So in order to get sub goals for the maze, you kind of need to derive your own sub goals by experience.
Yeah, I'm assuming I already know the structure of the maze. Then if based on that I come up with planning, it's possible to come up with some very detailed plan that I know must be done. Yeah.
Yeah, I mean, if the maze has different rooms, like room A, B, C, D, E, you can do planning by rooms first, like room A to room B, then room B to room C, and then room C to go. Yeah. So this is possible if you could split the grid into subspaces, which you might be able to learn from experience, or you might be able to chunk the learned trajectories together. This is something that cannot be done by LLMs, I believe, because LLMs don't have the grounding to the maze. This one needs to be done by trajectories. Still thinking about how to chunk trajectories together, but if you can do this, it'll be a very powerful means of planning because you can plan at a macro level by just chunking or some other method. Pity Shusha is not here because she's busy right now, but you can ask about the chunking next time. I think there's a way to do this chunking based on experience alone. I'm quite sure of it. Just haven't found a way to do it yet. Yeah. Okay, let's are you okay if I move on to the next one?
Yeah.
Yeah. Next one is about how to find out the right abstraction to use. Like what, so you said last week, like if you want to do like painting, you need to remember the input space, the pixel space. But if you want to do like interpreting what image is this, is it a dog or cat? Maybe you can go to the classification space, which is like all the way at the end, the abstract space. So what is the right hierarchy to use in order to like learn? What abstraction should we use to like maybe store the answers or store the experiences?
I think this is a very open-ended question. It all falls down, like for example, in traditional neural network, how they derive new architecture. So all based on domain knowledge, right? So like for the music one, Zhi and you were discussing previously, like you can actually represent it not the bottom up and top down, and Zhi has more musical experience, right? Then I guess you can experiment, you can represent in that way, but they also prove that you can represent it in just a top-down approach in the Jukebox AI, right? So yeah, I guess it all falls down to the domain knowledge. Like it's not exactly, you don't exactly have to find the right one, it's just a suitable hierarchy.
Yeah, actually I'm thinking there might be no way to disambiguate the different abstractions together, because if we talk about like abstractions being conditioned on one another, right? It could be very well that this abstraction space, this function fx, right? You need to take the entire thing wholesale. So you might not be able to like only learn the fine grain stuff. You might need to like learn the entire mapping from the fine to from this is like the fine grain, the fine grain to the coarse grain, which is the macro level concept, coarse grain. You might need to learn this entire set of memories or this entire set of abstractions, because all of them are conditional on each other. You need to learn the whole set. You cannot just take only, like, you can't really just take only this one here. I mean, to test this, let's think about our memories, okay? So if we talk about like, maybe we can think of a memory of, I don't know, the last time you walked to maybe to eat food, all right? So could you remember, like, as you walk to eat food, like you walk to a place to eat, what is like the kind of things you see, what are the things you see? So that's like more fine grain, I guess. Like, okay, maybe ask yourself, like, how do you walk there? So you could say, oh, I walked through an underpass, then I went up the staircase. Yeah, that's one thing. They can ask you like, why do you walk there? Then you will think like, oh, I walked there because I wanted to eat. So naturally, like we store our memories in the form of like how and why. You can go up and down the abstraction space just by like prompting yourself, like asking yourself how. How means go down one level, more fine grain. Why means you go up one level, more coarse grain. And it seems to me that like you take any memory, you can ask yourself how and why, and you can get an answer.
I would argue that that's because you already stored very detailed memory of that event or related to that event or the places. So if you, let's say if you only you went to like somewhere only once, then someone asking you a lot of questions about that place, you might not be able to answer some of the question, right?
Or you might be confabulating with some other places you've seen before.
Because like if you go to some place to eat, I assume like it's a very routine action, go to the same place to eat. Then you are kind of reinforced, like maybe the first time you didn't pay attention to something, then the second time you like you pay attention to that. So you already construct a very detailed mental image of the place. So you are able to answer a lot of different questions from different perspectives. Because you already had those details in your mind. But I would argue if like you only do something like the example you gave last time, the orientation of the mark, if you ask me to pay attention to that, I might ignore what pattern is on your mark.
Actually,
right?
so you made a very good point. Oh, so you want to say some more? I let you continue.
No, I think, yeah, that's my point. So
I think you make a very valid point, because we may not be able to retain this fine-grained information on first glance. It might take a while. So perhaps what will happen is our memories of the coarse grain will definitely be there, but we will only remember to a certain limit based on what attention you use. The more attention you use, the more you remember the fine-grained details. Like if you want to memorize a painting, you need to use all the memories in your brain, or rather all the neurons in your brain, most of it, to try to learn as much as possible about the picture. So this uses a lot of brain power. That's why probably in most cases, we don't remember so much. We only remember the very broad stuff because we have a limited brain capacity. We cannot compute so much. No power also. Like we need to eat to get power. Yeah. So the amount of attention you spend on a particular thing might determine like how much you remember. And
also, I was just reminded another point. So different from this example where you explicitly give me instruction on what to pay attention to, then I have the correct abstraction to answer your, like, to follow your instruction, right? Different from that, actually in reality, a lot of cases where it's not even straightforward for us to find a correct representation. For example, so I remember last time I played tennis with my friend. So even for my own experience, the first time you are just not able to play correctly because you don't know the technique. You don't know like the correct abstraction of what to focus. You need someone to teach you, to tell you. If without experiences, it's very hard to figure out what is a correct expression on the first try, right?
that's
So
true.
it's not, in a lot of situations, it's not even clear for us to know what is a correct expression for certain task. Yeah. So it's definitely not a trivial thing. Yeah.
Yeah, it's like, for example, I guess if you talk about music also, you know, like you want to play the piano, someone will need to tell you, okay, you need to focus on the fingers first, you know, practice your fingers so that later you can use these fingers to get the melody. If you like do by yourself, you might just use the same finger one by one, you know. So it's kind of true that, like, that's why instruction matters. Like learning from other people's behaviors help a lot. Learning from examples help us to know like what are the abstraction spaces that are most crucial for the task.
Yeah, so it's really domain knowledge. Like it's a lot of times it's just not clear what is the correct abstraction or the correct biases to use.
Yeah, like when I play video games, sometimes I cannot like get past a level, and I go and see the walkthrough. And after the walkthrough, I know how to do different levels that are similar already. But that's because I maybe didn't pay attention to this particular thing in the game. Yeah, and this thing is important for that level. Yeah, so I agree with you. So it's very interesting. It means that if you don't have someone to cue you the right level of abstraction, you will need a long time before you discover it, or you may not even discover it at all.
Yeah, very likely, I would say. Especially for very highly skilled tasks.
Yeah. So it seems to be this abstraction, like the way we disambiguate this abstraction, might be given rather than learned. For some tasks, it might be given. Like someone must tell you what are the abstractions, then you focus on the right thing.
But if you want to learn, then it's highly non-trivial.
Yeah. So perhaps if there's no way to solve all problems at once, but you need to, there's a generic approach that can solve most problems, but for all kinds of problems, you probably cannot just use the same architecture. I mean, you can use the same architecture, but you will need some external guidance for all kinds of problems. You cannot just like natively learn everything yourself. Yeah, I think that's the key point that we are getting at. Yeah, interesting.
Yeah,
interesting.
remind me of the inductive biases of CNN also. Like without the knowledge from physics on things like translational invariance, how do you even come up with such an architecture? Like, yeah. So.
All right, let's sit on this a bit more. I think this is a very important point. Like eventually, we need to answer this question because a system that is self-learning, or rather a system that learns from your own experiences, you kind of need to find out this abstraction yourself. If not, you need to have a group of systems or multi-agent system that each of them maybe try a different abstraction space to solve the problem. And if one of them solve, they share their knowledge. So I think this we can revisit next time when we talk about group intelligence. All right, let's talk about the last question. But thanks for sharing, Sari. I think it's very insightful. I learned a bit also from all this. Yeah, I never thought of it this way. Right, the last one, should we represent the abstraction space or latent space as continuous or discrete? So, for LLMs, the tokens are discrete. But for like reinforcement learning, the continuous actions, we can talk about continuous actions. Like if you want to do prediction, can we just predict discrete stuff? Because, discrete stuff is easier to predict. You have fewer cases. It's easier to get a classification on discrete number of categories. Yeah. So the question is, can you represent like maybe continuous actions by a sequence of discrete tokens? Maybe you could do like vector quantization. You could do like A plus B plus C, where like A more coarse grain, B medium, and then C is fine grain. Yeah, so perhaps we could do actions by discrete stuff as well. And the question is, would an unbounded length of these discrete tokens be sufficient to represent continuous spaces? Because if we can do discrete representation, we may be able to like do everything by transformers. Because right now, transformers, to do the tokenization, you need to do it as the discrete token, unless you don't tokenize at all. I mean, there are mechanisms that bypass the tokenization step altogether. You can just feed in the continuous number straight away. Yeah, but then you might lose out on the meaning of the continuous variable. So the question is, can we just use discrete tokens to represent everything?
I think this is problem specific again. The main difference between the two is, I guess, maybe don't call it continuous, because continuous implies infinite, right? Maybe a very large range of discrete, like unbounded length of discrete maybe is better. And the thing that it impacts is of course the learning capacity of your network or your transformer. If you're using a slightly longer or much longer length of discrete tokens, you are able to ideally represent more distinct tokens, right? Like what you were saying, you're not losing too much fidelity in the meaning. So in that sense, in theory, the learning capacity of the network should be increased compared to, let's say, a much smaller bound in the length. But then, as I think we were discussing on representations, is there actually a need to have such a much wide difference between the respective tokens? Maybe you can cheat a bit and then you have a shorter discrete range, and that shorter discrete range should already be able to extract the relevant meaning in your problem. Then you should, linking back to what Occam's razor and what minimum description length in machine learning, you should choose the one of the more simplified tokens.
Yeah, actually I agree. Like in Kato, for continuous domains, like for some Mujoko environments with some robots, they actually use this thing called mu law encoding or discretization, where you basically discretize the states that are nearer to the zero mark. You discretize them in more fine grain, and then towards the larger part, you discretize them in more coarse grain. So something like this could be a proxy for continuous variables, because for most of the time, like even for hand actions, the fine-grained things matter a lot. But then once you get beyond the fine-grained things, the more macro ones, you don't really need to like control fine-grained very well. You can just like do the medium level stuff here. So you just need to do the very fine-grained stuff well, and the very broad range one you can just do in an approximation. So I do think that, yeah, you can represent continuous by discrete, and in so doing, simplify the problem a lot. Yeah, and again, you can lead to like perhaps reuse, because like if you were to represent your continuous action by like a sum of different actions, you could perhaps do it by a hierarchical action. Like for example, you take A here, then you take the residual, then you get B, then you take the residual, you get C. You could perhaps like do some form of prediction at all levels here. So you can predict the coarse grain, predict the medium grain, predict the fine grain. Right? So I think this is one way of doing it. Personally, I prefer to represent everything as discrete, because I mean, even stuff like information theory kind of breaks down with infinite number of tokens. Like continuous domains, the way you like discretize it will lead to different information, lead to different mutual information calculations. And it's not ideal. So if you could represent the world with discrete outcomes, it will be very, very beneficial in terms of your abstraction space. This is what I believe in. Yeah. Again, no math here. It's just it's currently still in terms of idea formulation. Yeah, but thanks, Dylan. I tell you have anything else to say for this?
Not really.
Okay, if not, actually, that's all I have to discuss. Any last comments before we end today? Yeah, if not, thanks for staying so long. I know it kind of exceeded the time, but today was really very insightful for me. And yeah, thanks so much for the discussion. Yeah, I'll be stopping now. Okay, bye.